Alright, for this last and final video, did you catch that repetition? Redundancy. For this last video, we need to talk about decay. Remember, we talked about our nucleus before. This was in a previous video. This nucleus, there's a very delicate balance of protons and neutrons because the protons and neutrons, their balance contributes to the balance between the electrostatic force and the strong nuclear force. Remember, the electrostatic force is the one that wants to blow the nucleus apart. Strong nuclear force keeps it intact, and there's a balance between those two based on the mass of the nucleus, the size of the nucleus, and how many protons and neutrons there are. And so isotopes, there are isotopes of different elements that simply have more neutrons, right? Doesn't have more protons, doesn't have more electrons, but it has more neutrons. They're useful, but there being more neutrons, what's happening is we're messing with the relative amounts of electrostatic and strong nuclear force. The more neutrons there are, the stronger the strong nuclear force is. And for that reason, and probably some others, it makes the nucleus unstable. It doesn't want to be that way. So there's actually quite a few different ways probably that the nucleus can become unstable, but these are the main two that happen. Alpha decay and beta decay, and you learned about these in chemistry, I think. So a nucleus can undergo alpha decay or beta decay in order to become more stable. In alpha decay, what happens is we get 2 protons and 2 neutrons released from a large unstable nucleus, and those protons and neutrons, they leave. They go away at a actually kind of high rate of speed. It's actually very low energy radiation that happens here, but they go away so they're released from that nucleus. They go away. In beta decay, what happens is that there's a neutron, and a neutron gets split into a proton and an electron. So the neutron goes away, it becomes a proton and electron. The electron gets ejected, relatively low energy, ejected from the atom. It's gone. The proton stays. Proton stays in the nucleus. The electron goes, because obviously electrons are not nuclear particles. They're not nucleons. Both types, alpha and beta decay, the atom becomes a different element, because with both types you're messing with the number of protons. When you change the number of protons, you change what the element is. So this is our chemical symbol. We know that this is the symbol for the element symbol that you have. It happens to be uranium in this one. Remember that the top number was called the mass number. That doesn't represent exactly the mass of the element. It's close, but it's not exact. And the bottom number was called the atomic number. Remember that the mass number represents the number of protons plus the number of neutrons. Protons plus neutrons. And the bottom number represents just the number of protons. So top number, protons plus neutrons, mass number. And remember, protons and neutrons are collectively referred to as nucleons. So we can just say that the top number represents the number of nucleons. The mass number represents the number of nucleons. And the reason why we call it the mass number is because protons and neutrons are what contribute to the mass of the element. Atomic number, obviously, number of protons. So you won't be required to write these chemical symbols, but you will be required to recognize them. So let's talk about alpha decay. Remember, with alpha decay, what happens is from inside the nucleus, we get 2 protons and 2 neutrons that are released. They get ejected, they go away. And so what we need to do is think about what happens to the numbers, to each of these numbers. Mass number in this one is 222. It's radium. This represents the number of nucleons. Well, we lost 4 nucleons. We lost 2 protons and 2 neutrons. 2 plus 2 is 4. So this number goes down by 4. 222 minus 4 is 218. Bottom number, the atomic number, is the number of protons. We lost 2 of those. 88 minus 2 is 86. And the 86th element happens to be radon. So radium decays into radon is what we say, but then we have to account for the nucleons that we lost. We account for that over here. Again, 4 nucleons, the top number is 4. 2 of them are protons, the bottom number is 2, and the second element is helium. This is what we call the alpha particle. That's the alpha particle, and you get this every single time, always, with alpha decay. When you get alpha decay, this is what you're looking for. It doesn't matter what these 2 elements are, and they can be different, but the point is you always get a difference in 4 here, a difference in 2 here. Therefore the alpha particle is helium. That's what gets ejected. It's a helium nucleus. Beta decay, on the other hand, we start with a neutron. Neutron goes away and becomes a proton and an electron. And remember, the electron gets ejected, proton stays put. So we have to think about what happens with these numbers. 14, the mass number, represents the number of nucleons. We lost a proton, so we lost a nucleon, but we lost a neutron, lost a nucleon, gained a proton, so we gained a nucleon. So we lost one and we gained one, therefore the net change is 0, therefore this number stays the same, it remains 14. So mass number is still 14. Atomic number, protons down at the bottom, we gained one proton, so 6, we add 1 to it to become 7, and the 7th element is nitrogen, right? So carbon decays into nitrogen through beta decay, but we have to account for the electron. The electron is over here, and we symbolize it like this. This is what we referred to as the beta particle. Beta particle is what gets ejected from the nucleus, and this you always have with beta decay. That's the Greek symbol, Greek letter beta. It's like a capital B with a funky tail in the front. So you need to be able to recognize these equations, and that's nuclear physics.